So now take a function f of two variables defined in an open region containing this point AB. Now we will call that function differentiable at AB if the partial derivatives with respect to x and that with respect to y, they exist at AB, and the limit of this quantity goes to 0, and the quantity is what we have is that you can see we have the function fxy, and then we are going to after that focus on this portion here, this linear function. All right, so we will see that we can bring the function as close as we would like to this linear function in the vicinity of the point AB. All right, so let me show you some examples, all right, and proceed through that. So we are taking this simple example. So let me take an example of a polynomial, okay, and which will be a paraboloid. All right, so let's take x squared plus y squared as our fxy, and the point where we would like to verify is say 1 1. So this is defined in an open region containing 1 1, and we want to see if it's differentiable at 1 1. So you can see we will just go by the mechanical procedure, that is x squared plus y squared. The partial derivative with respect to x is 2x, and that with respect to y is 2y. So they exist everywhere, and they exist at 1 1 as well. Okay, now when we go to compute the limit, and let me remove this because this is what we want to prove. So xy goes to 1 1, and here our function is x squared plus y squared. F at AB is what? This function at 1 1, so that will be 1 squared plus 1 squared, that is 2. So this part is 2. Then the partial derivative at 1 1 is how much? Substitute x equals 1, you get a 2. Then a is 1. Right here the partial derivative with respect to y at 1 1 again is 2, and for b we have 1. Let's change these guys to 1 and 1. So what happens now is that this whole thing is equal to, okay, so we have -2 when we distribute on the brackets. This will become a +2, right? And then we will have another +2, right? So then what happens next is that this 2, or this -2 and this +2 will cancel each other. And now what we can do is that we can rearrange these steps. Okay, so here, remember this is how you did, parabolas in one variable calculus. So I moved y squared there with y, and for 1 I'm splitting this as 1 plus 1 here just to complete these squares. So this portion becomes x minus 1 squared, and this portion becomes y minus 1 squared, right? So you got x minus 1 squared here, okay, that is this quantity here, and then y minus 1 squared here. So what will happen after you simplify this, then this is the limit, or let me just take it to the next line. Okay, so this is the limit of what? this quantity divided by its positive square root, so that will be the limit of the square root of the quantity, which will be 0. Okay, so this was a straightforward example in which we could do algebra easily. And notice this, that here if you look at this numerator or this portion, or let me just show you geometrically or graphically what's going on. Okay, so geometrically it is like this, that say this is the graph of x square plus y square, and this is the graph of say Lx y equals 2x plus 2y minus 2, a linear function. Then when x is 1, y is 1, z will be what? 2. So at 1, 1, 2, that at this point, this is this plane and this curve, as you can see. So let me show you here in the original window that these two can be brought as close to each other, or we can bring this red graph close to this gray graph, as close as we would like by staying sufficiently close to this point 1, 1, 2, which is the same as, if you recall, that when you had one variable calculus, say you took a function y equals gx, say x square, right? The function is differentiable at 1, 1. So this is the graph of the function, or a graph of the function x square. This is the point 1, 1. And this line is 2x minus 1. And this parabola is, we can bring this graph of parabola as close to the graph of this line near the point 1, 1 as we please by staying close enough to the point 1, 1. Okay.